Imagine looking back in time 13 billion years to when the universe was just a baby. Imagine seeing the very first galaxies being born, watching stars ignite for the first time, and discovering worlds we never knew existed. This is exactly what the James Webb Space Telescope has been doing since it started sending data back to Earth in 2022. In just 2 years, this incredible machine has revolutionized our understanding of the cosmos, challenged our most fundamental theories, and revealed that the universe is far stranger and more beautiful than we ever imagined. If you're fascinated by these cosmic mysteries and want to explore the universe's greatest secrets, make sure to subscribe to this channel and give this video a thumbs up. And one quick question: if you could rewrite one law of physics, which would you change, and how would it transform the universe? Drop your answer in the comments below. I'll pin the most creative answer. Now let's begin. The James Webb Space Telescope, or JWST as astronomers call it, isn't just another telescope, it's a time machine. Its massive 6.5-meter mirror, made of 18 hexagonal segments coated in gold, can capture light that has been traveling through space for over 13 billion years. That means when we look through Webb's eyes, we're seeing the universe as it was when it was less than 400 million years old, just 3% of its current age. But before we dive into the discoveries, let me tell you why Webb is so special. Unlike the Hubble Space Telescope, which primarily sees visible light and some ultraviolet, Webb observes in infrared. This is crucial because light from the most distant objects in the universe gets stretched by the expansion of space itself, shifting from visible light into infrared. It's like the universe is speaking in a language only Webb can fully understand. The telescope sits at a special point in space called Lagrange Point 2, or L2, about 1.5 million kilometers from Earth. At this spot, the gravitational forces of Earth and the Sun balance perfectly, allowing Webb to stay in a stable position while keeping its back to the Sun. Its tennis court-sized sunshield blocks all the heat and light from the Sun, Earth, and Moon, allowing the telescope to cool down to -233 degrees Celsius. At these frigid temperatures, Webb can detect the faintest whispers of infrared light from across the cosmos. Now let's talk about the discovery that shocked the entire astronomical community and made headlines around the world. In July 2022, just weeks after Webb started its science operations, it spotted something that shouldn't exist according to our models: massive, mature galaxies that formed when the universe was incredibly young. The galaxy called Glass Z12 was seen as it existed just 350 million years after the Big Bang. But here's what's mind-blowing. This galaxy was already massive and surprisingly mature. It's like finding a fully grown oak tree in a nursery full of seedlings. According to our understanding of how galaxies form, there simply hadn't been enough time for such massive structures to develop. Then came JD's GSY 13-0, which pushed the record even further back, existing just 325 million years after the Big Bang. These discoveries weren't flukes. Webb kept finding more and more of these impossible early galaxies. Some of them contained hundreds of millions of stars, all formed in the universe's infancy. This discovery is forcing astronomers to completely rethink how galaxies form. The standard model suggested that galaxies grew slowly, starting small and gradually merging and accumulating mass over billions of years. But Webb is showing us that the early universe was far more efficient at building galaxies than we thought possible. It's like discovering that ancient civilizations had technology we thought was invented much later. It changes the entire timeline of cosmic history. But why does this matter to you? Well, those early galaxies are your cosmic ancestors. The processes that formed them set the stage for everything that came after, including our own Milky Way galaxy, our Sun, and ultimately, Earth and life itself. Every atom in your body, except for hydrogen, was forged in the nuclear furnaces of stars that lived and died in galaxies. Understanding how the first galaxies formed helps us understand our own origins. Webb didn't stop there. It's been peering into stellar nurseries, the cosmic clouds where stars are born, with unprecedented clarity. The telescope revealed something extraordinary in the Orion Nebula: brown dwarfs, failed stars that aren't massive enough to sustain nuclear fusion, floating freely through space. But here's the weird part. Many of these brown dwarfs exist in pairs, orbiting each other in a cosmic dance. These binary brown dwarfs shouldn't exist according to our theories. They're too small to have formed like stars, but they're also in the wrong place to have formed like planets. It's as if nature found a third way to create celestial objects that we never imagined. Some astronomers are calling them jumbos, Jupiter mass, binary objects, and they're scrambling to understand how they came to be. In the Carina Nebula, one of the most spectacular star-forming regions in our galaxy, Webb revealed jets of material shooting out from baby stars at hundreds of kilometers per second. These jets, called Herbig-Haro objects, are like cosmic birth announcements, signaling the arrival of new stars. Webb showed us these jets in incredible detail, revealing shock waves and bow shocks as the fast-moving material slams into the surrounding gas. But perhaps the most stunning stellar nursery image came from the cosmic cliffs in the Carina Nebula. This three-dimensional wall of gas and dust, sculpted by intense radiation from young stars, looks like a cosmic mountain range. In this single image, we can see hundreds of previously hidden stars being born, some still wrapped in their cocoons of dust and gas. It's like watching a cosmic maternity ward where hundreds of stellar babies are taking their first breaths. Now let's talk about one of Webb's most mind-bending discoveries, the oldest and most distant galaxies ever observed. Using a technique called gravitational lensing, where massive galaxy clusters act like cosmic magnifying glasses, Webb has spotted galaxies from when the universe was just 2% of its current age. The galaxy cluster Hubble 2744 acted as nature's telescope, bending and magnifying light from galaxies behind it. This allowed Webb to see Glass Z12 and other incredibly distant galaxies that would otherwise be too faint to detect. It's like the universe is helping us see its own baby pictures, using gravity itself as a lens. These observations are revealing something unexpected about the early universe. It was much more organized than we thought. The first galaxies weren't just random collections of stars. They had structure, including spiral arms and central bulges, features we thought took billions of years to develop. Some even show signs of having central supermassive black holes, which raises huge questions about how such massive objects could form so quickly. Speaking of black holes, Webb has been revolutionizing our understanding of these cosmic monsters. In 2023, it discovered the most distant active supermassive black hole ever seen, existing just 570 million years after the Big Bang. This black hole in the galaxy Sears 1019 has a mass of about 9 million suns. That's absolutely huge for something so early in cosmic history. The existence of such massive black holes so early in the universe is like finding a full-grown elephant where you expected to find a mouse. It suggests that the first black holes either formed from the direct collapse of massive gas clouds, skipping the star phase entirely, or they grew incredibly fast through some unknown mechanism. Either way, it's forcing us to rewrite the textbook on black hole formation. Webb has also been studying how galaxies interact and merge, showing us cosmic collisions in unprecedented detail. It captured the Cartwheel Galaxy, which looks like a cosmic wagon wheel created by a head-on collision between two galaxies. The collision sent a shock wave rippling outward, triggering star formation in a perfect ring. Webb's infrared vision pierced through the dust to reveal previously hidden star-forming regions and the complex structure of the galaxy's spokes. These galactic collisions aren't just spectacular light shows, they're fundamental to how galaxies evolve. In fact, our own Milky Way is on a collision course with the Andromeda Galaxy. If you want to learn more about what will happen when these two galactic giants meet in about 4 billion years, check out my video called "What Will Happen When the Milky Way Collides with Andromeda?" It's a mind-blowing look at our galaxy's future and how these cosmic crashes actually create rather than destroy. The link is in the description and on the card above. But Webb isn't just looking at galaxies, it's also revolutionizing our understanding of exoplanets, worlds, orbiting other stars. One of its most exciting discoveries came from the TRAPPIST-1 system, where 7 Earth-sized planets orbit a small red dwarf star just 40 light-years away. Webb detected the atmosphere of TRAPPIST-1b, the innermost planet, and found something surprising, or rather, didn't find something. The planet has no substantial atmosphere despite being rocky like Earth. This was unexpected because scientists thought the planet might have a thick atmosphere of carbon dioxide. Instead, Webb showed that this world is a bare rock, scorched by its star's radiation. But the real excitement came when Webb studied TRAPPIST-1c. This planet showed hints of a possible atmosphere, though a very thin one. The data suggests it might have a Venus-like atmosphere dominated by carbon dioxide. This is crucial because understanding which planets can hold on to their atmospheres helps us figure out which worlds might be habitable. Then came the bombshell discovery from planet K2-18b, a world 8.6 times the mass of Earth orbiting in the habitable zone of its star. Webb detected something incredible in its atmosphere: methane and carbon dioxide, but mysteriously no ammonia. This chemical signature suggests something extraordinary. K2-18b might be a Hycean world covered in a global ocean with a hydrogen-rich atmosphere above it. But here's what made scientists really sit up and take notice. Webb might have detected dimethyl sulfide, or DMS, in the atmosphere. On Earth, DMS is only produced by living organisms, mainly phytoplankton in the oceans. While the detection isn't confirmed yet if it's real, it could be the first hint of biological activity on another world. Let me be clear though, we're not claiming we've found life. Science doesn't work that way. What we've found is a tantalizing hint, a possibility that needs much more investigation. But the fact that Webb can detect these biosignatures at all is revolutionary. For the first time in human history, we have the technology to search for signs of life on distant worlds by analyzing the chemistry of their atmospheres. Webb has also been studying hot Jupiter's massive gas planets that orbit incredibly close to their stars. The planet WASP-39b showed Webb's incredible capabilities when the telescope detected water vapor, sodium, potassium, carbon monoxide, carbon dioxide, and even clouds and hazes in its atmosphere. This was the most detailed analysis of an exoplanet atmosphere ever achieved, but here's where it gets even more interesting. Webb found that WASP-39b has sulfur dioxide in its atmosphere, the same compound that creates acid rain on Venus and volcanic smog on Earth. This is the first time sulfur dioxide has been detected in an exoplanet atmosphere, and it's only there because of photochemistry, like chemical reactions driven by starlight. It's like finding out that alien worlds have their own version of smog created by the interaction between their star's light and their atmosphere. The diversity of exoplanets Webb is revealing is staggering. Some have clouds made of silicate, essentially clouds of vaporized rock and sand. Others have atmospheres so hot that they rain liquid iron. The planet WASP-96b showed signs of clouds and hazes that weren't expected, proving that even planets we thought we understood can surprise us. But Webb isn't just looking at distant stars and galaxies, it's also transforming our understanding of our own solar system. When it turned its golden eye toward Jupiter, it revealed auroras at both poles that dwarf anything we see on Earth. These auroras, caused by charged particles from the Sun interacting with Jupiter's magnetic field, extend high above the planet's cloud tops and glow brilliantly in infrared light. Webb also captured Jupiter's faint rings, which are 1,000,000 times dimmer than the planet itself. These rings, made of tiny dust particles, tell us about the small moons and asteroids that created them through countless impacts. It's like reading the history of collisions in our solar system, written in dust and ice. At Saturn, Webb made an unexpected discovery about the moon Enceladus. This small, icy moon shoots geysers of water vapor into space from its subsurface ocean. Webb detected a massive plume of water vapor extending more than 6,000 miles from the moon. That's nearly the distance from Los Angeles to London. This plume feeds Saturn's E-ring and could contain organic molecules from the ocean below. Why is this exciting? Because Enceladus's ocean, hidden beneath its icy shell, is one of the most promising places to search for life in our solar system. The fact that this ocean water is being shot into space means we don't need to drill through miles of ice to sample it. Enceladus is literally spraying its ocean into space for us to study. Webb also observed Titan, Saturn's largest moon and the only moon in our solar system with a thick atmosphere. It captured clouds moving across Titan's surface and confirmed seasonal changes in its atmosphere. These aren't water clouds like on Earth, they're made of methane and ethane. On Titan, methane plays the role that water plays on Earth, forming clouds, falling as rain, and creating rivers and lakes. Moving to the outer reaches of our solar system, Webb studied Neptune and its mysterious moon Triton. Neptune showed bright clouds in its atmosphere, including a band of clouds surrounding its south pole that had never been seen so clearly before. These clouds are made of frozen methane crystallizing in Neptune's frigid upper atmosphere, where temperatures drop to -200 degrees Celsius. But perhaps Webb's most surprising solar system discovery came from studying asteroids. The asteroid Chariklo, which orbits between Saturn and Uranus, was found to have 2 thin rings around it. Even more amazingly, Webb detected crystalline water ice on these rings. This was completely unexpected. Astronomers thought radiation from the Sun would have turned any ice into an amorphous, non-crystalline form over millions of years. The presence of crystalline ice suggests that either the rings are very young or something is constantly refreshing the ice. Now let's talk about one of Webb's most beautiful and scientifically important targets, planetary nebulae. These aren't actually planets at all, but the dying gasps of stars like our Sun. When a star runs out of fuel, it puffs off its outer layers, creating these gorgeous, colorful shells of gas. Webb observed the Southern Ring Nebula and revealed something nobody expected. The dying star at its center has a companion. This companion star is orbiting within the nebula itself, shaping the gas with its gravity and stellar wind. The images show at least 2 and possibly 3 shells of gas ejected at different times, telling us the story of the star's death throes over thousands of years. In the Ring Nebula, one of the most famous objects in astronomy, Webb revealed intricate details never seen before. It showed about 20,000 dense clumps of gas, each about as massive as Earth, formed in the outer shell of the nebula. These clumps are like cosmic hailstones, condensing from the hot gas as it expands and cools. Webb also detected large carbonaceous molecules called polycyclic aromatic hydrocarbons, the same molecules that might have delivered the building blocks of life to early Earth. These dying stars are showing us our own future. In about 5 billion years, our Sun will go through the same process, puffing off its outer layers and creating its own planetary nebula. The carbon and oxygen and nitrogen that make up your body will one day be part of such a nebula drifting through space, ready to become part of new stars and planets. Webb is literally showing us how stellar death leads to cosmic rebirth. But one of Webb's most profound discoveries involves something we can't even see: dark matter and dark energy. By studying how galaxy clusters bend light from more distant galaxies, Webb is mapping the invisible dark matter that makes up 85% of all matter in the universe. The galaxy cluster, SMACS 0723, featured in Webb's very first deep field image, acts like a gravitational lens, distorting the images of thousands of galaxies behind it. By analyzing these distortions, astronomers can map where the dark matter is, even though we can't see it directly. It's like mapping wind by watching how it moves leaves. We can't see the wind itself, but we can see its effects. Webb's observations are showing that dark matter is distributed in complex webs and filaments, creating the cosmic scaffolding that galaxies form along. Webb is also tackling one of the biggest mysteries in cosmology: the Hubble tension. This is the troubling disagreement between different methods of measuring how fast the universe is expanding. When we measure the expansion rate using the cosmic microwave background, the afterglow of the Big Bang, we get one number. When we measure it using supernovae and variable stars in nearby galaxies, we get a different, higher number. This isn't a small discrepancy, it's a fundamental problem that suggests we're missing something important about how the universe works. Webb is helping by providing incredibly precise measurements of Cepheid variable stars, which astronomers use as standard candles to measure cosmic distances. So far, Webb has confirmed that the Hubble Space Telescope's measurements were correct, which means the tension is real, not just a measurement error. This might seem like an abstract problem, but it could revolutionize physics. The Hubble tension might be telling us that dark energy, the mysterious force causing the universe's expansion to accelerate, changes over time. Or it might mean there's some entirely new physics we haven't discovered yet. It's like finding that your GPS and your speedometer disagree about how fast you're going. It means something fundamental is wrong with our understanding. Webb has also been studying the cosmic dawn, the period when the first stars lit up the universe. For the first few 100 million years after the Big Bang, the universe was dark. There were no stars, no galaxies, just vast clouds of hydrogen and helium gas. Then gravity began pulling this gas together, and the first stars ignited. These first stars were monsters, possibly hundreds of times more massive than our Sun. They burned hot and bright and died young, exploding as supernovae after just a few million years. Webb hasn't directly observed these population 3 stars yet. They're probably too faint even for its powerful vision, but it's seeing their effects. The early galaxies Webb observes show chemical signatures suggesting they contain second-generation stars formed from gas enriched by those first stellar explosions. Understanding this cosmic dawn is crucial because it's when the universe transformed from a dark, simple place to the complex, star-filled cosmos we see today. It's when the first heavy elements were forged, when the first black holes formed, and when the seeds of all future structure in the universe were planted. Every galaxy, star, and planet today is a descendant of processes that began during the cosmic dawn. Webb has also revolutionized our understanding of how elements spread through the universe. When it observed the galaxy NGC 7469, it detected fluorine in a star-forming region. Fluorine is interesting because we weren't sure how it forms. It could come from massive stars, or from the explosive deaths of intermediate mass stars called asymptotic giant branch stars. Webb's observations suggest both processes contribute, solving a long-standing cosmic mystery. Think about that for a moment. Fluorine is in your toothpaste, helping protect your teeth. Webb is showing us exactly how that fluorine was created in the nuclear furnaces of dying stars. Billions of years ago, you're literally brushing your teeth with stardust, whose origin story we're just now understanding. But perhaps one of Webb's most beautiful discoveries is about cosmic dust itself. This might sound boring. After all, dust is just dust, right? Wrong. Cosmic dust is incredibly important. It's the raw material from which planets form. It shields stellar nurseries from radiation, allowing new stars to form, and it carries complex organic molecules through space. Webb can see through dust that blocks visible light, revealing hidden treasures throughout the universe. In the galaxy NGC 604, Webb revealed star-forming regions completely hidden from Hubble's view. These regions are creating new stars at a furious rate, but they were invisible to us until Webb's infrared vision pierced the cosmic veil. The telescope also discovered that dust forms much earlier in the universe than we thought. Galaxies from when the universe was less than 1 billion years old already contained significant amounts of dust. This is surprising because dust is made of heavy elements that must first be created in stars. The fact that early galaxies are already dusty tells us that the first generations of stars lived and died even faster than we imagined. Webb's study of cosmic dust revealed something even more fascinating: complex organic molecules in the most unlikely places. In the protoplanetary disk around the young star ISO Chi 147, Webb detected methane, ethane, carbon dioxide, and water vapor. But here's the kicker: it also found benzene, a ring-shaped molecule that's a building block for more complex organic chemistry. Finding benzene in a planet-forming disk is huge. On Earth, benzene is part of DNA, proteins, and many other biological molecules. While finding benzene doesn't mean finding life, it shows that the chemical ingredients for life are present in planetary systems from the very beginning. It's like finding out that nature pre-stocks planetary nurseries with the Lego blocks needed to build life. Webb has also been revealing the secret lives of red dwarf stars, the most common type of star in the universe. These small, cool stars make up 75% of all stars, and they can live for trillions of years, far longer than the current age of the universe. If we're going to find life elsewhere, statistically speaking, it's likely to be on a planet orbiting a red dwarf. But red dwarfs have a dark side. They're prone to violent flares that could strip away planetary atmospheres and sterilize any life. Webb observed the red dwarf star AU Microscopii and caught it in the act of flaring. The flare was so powerful it would have delivered hundreds of times more ultraviolet radiation to any orbiting planets than Earth receives from the Sun during its worst storms. However, Webb also found something encouraging. Some planets around red dwarfs, like LHS 475b, show signs of having atmospheres despite the stellar violence. This suggests that at least some planets can hold on to their atmospheres and potentially remain habitable even around these temperamental stars. It's like finding out that some houses can withstand hurricanes. It gives us hope for finding habitable worlds in unexpected places. One of Webb's most mind-bending discoveries involves time itself. Because light takes time to travel across the universe, looking at distant objects means looking back in time. Webb has pushed this to the extreme, observing galaxies as they were over 13 billion years ago. But here's where it gets weird. Some of these ancient galaxies look too modern. The galaxy JWST 701012, besides having a name only an astronomer could love, shows a structure that shouldn't exist so early. It has a disk with spiral features, a central bulge, and even what might be spiral arms. According to our models, galaxies in the early universe should be small, chaotic blobs. Instead, Webb is showing us galaxies that look surprisingly like nearby galaxies, just smaller and forming stars much faster. This is forcing astronomers to rethink galaxy evolution entirely. Maybe galaxies can organize themselves much faster than we thought. Maybe dark matter plays a different role than we assumed. Or maybe there's some unknown process that fast-tracks galaxy formation in the early universe. It's like archaeologists finding ancient cities with modern urban planning. It suggests our ancestors were more sophisticated than we gave them credit for. Webb has also discovered that supermassive black holes might have a speed limit on their growth. By studying quasars, galaxies with actively feeding black holes at their centers, Webb found that black holes can only grow so fast before their own radiation chokes off their food supply. It's like trying to drink from a fire hose. At some point, the pressure pushes back and stops you from drinking more. This discovery helps explain why we don't see black holes that are even more massive than the monsters we observe. The universe has a built-in regulatory mechanism that prevents black holes from growing indefinitely. This cosmic speed limit might also explain why most galaxies have black holes that are proportional to their size. There's a feedback mechanism that keeps black holes and their host galaxies in balance. Speaking of balance, Webb has revealed that the universe is remarkably good at recycling. When it observed the supernova remnant Cassiopeia A, it found pristine dust grains that survived the stellar explosion. This was unexpected. Astronomers thought supernova shockwaves would destroy any dust in their path. Instead, some dust survives and gets recycled into new generations of stars and planets. This cosmic recycling is incredibly efficient. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of these atoms have been recycled through multiple generations of stars. Webb is showing us exactly how this recycling process works, from the death of one star to the birth of others. We're not just made of stardust, we're made of recycled stardust that's been through cosmic processing plants multiple times. Webb has also solved a mystery about the universe's reionization epoch. After the Big Bang, the universe was filled with neutral hydrogen that blocked most light. Then something ionized this hydrogen, making the universe transparent. But what provided the energy for this cosmic clearing? Webb found the answer: dwarf galaxies. These small galaxies, containing just millions of stars instead of billions, turn out to be incredibly efficient at producing ionizing radiation. Webb showed that dwarf galaxies in the early universe leaked far more ionizing photons into space than expected. They're like cosmic leaf blowers clearing away the fog that filled the early universe. Without these humble dwarf galaxies, the universe might have remained opaque far longer, delaying the formation of the cosmic structures we see today. This discovery about dwarf galaxies is particularly meaningful because it shows that even the smallest players in the cosmic drama can have profound effects. These tiny galaxies, which would be barely visible in most telescopes, literally changed the entire universe. It's a cosmic reminder that size doesn't always determine importance. Sometimes the smallest things make the biggest difference. Webb has also been revealing the hidden chemistry of the universe. In the Orion Bar, a region at the edge of the Orion Nebula, Webb detected methyl cation CH3+ for the first time in space. This might sound like just another molecule, but it's actually a crucial piece of the cosmic chemistry puzzle. Methyl cation is a key intermediate in forming more complex carbon-based molecules, the kinds that life depends on. Finding this molecule helps us understand how simple carbon and hydrogen atoms in space eventually become the complex organic molecules we find in meteorites and comets. It's like finding the missing link in cosmic chemistry, showing us how the universe builds complexity from simple ingredients. Every organic molecule in your body has a history that likely included methylcation as an intermediate step billions of years ago. But Webb's discoveries aren't just about looking back in time, they're also helping us understand where the universe is heading. By studying Type Ia supernovae with unprecedented precision, Webb is helping astronomers measure the acceleration of cosmic expansion. These stellar explosions serve as standard candles because they all shine with roughly the same brightness, allowing us to calculate their distance. Webb's observations show that the universe's expansion is indeed accelerating, driven by the mysterious dark energy. But more importantly, Webb's precise measurements are helping us understand whether dark energy is constant or changing over time. Early results suggest dark energy might not be as simple as Einstein's cosmological constant. It might be dynamic, changing as the universe evolves. This has profound implications for the ultimate fate of the universe. If dark energy remains constant, the universe will expand forever, growing colder and emptier until all stars burn out in the far future. But if dark energy is changing, other scenarios become possible, including the terrifying Big Rip, where the expansion eventually tears apart galaxies, stars, planets, and even atoms themselves. Webb has also discovered that planet formation is messier and more violent than we imagined. In the protoplanetary disk around the star Beta Pictoris, Webb revealed a massive debris cloud from a catastrophic collision between asteroids. The amount of dust suggests the collision involved bodies hundreds of kilometers across. Imagine an impact that would make the asteroid that killed the dinosaurs look like a pebble toss. These observations show that young planetary systems are cosmic demolition derbies, with massive collisions shaping which planets survive and which are destroyed. Our own Earth likely experienced such collisions, including the impact that formed our Moon. Webb is showing us that planetary formation isn't a gentle process of gradual accumulation. It's a violent series of crashes that determines which worlds make it to maturity. In another young system, PDS-70, Webb caught planets in the act of forming. It detected spiral features in the protoplanetary disk that are almost certainly caused by baby planets carving paths through the dust and gas. It's like watching tire tracks form in fresh snow. We can't see the planets directly yet, but we can see their gravitational influence on their surroundings. One of Webb's most unexpected discoveries came from studying brown dwarfs, failed stars that weren't massive enough to sustain fusion. Webb found that many brown dwarfs have weather systems with silicate clouds, iron rain, and even possibly diamond dust. The brown dwarf VHS 1256 shows evidence of patchy clouds made of tiny grains of sand, creating weather patterns unlike anything in our solar system. Imagine a world where it rains liquid iron and snows microscopic diamonds, where clouds of vaporized rock create spectacular sunsets in alien colors. These bizarre worlds exist by the thousands in our galaxy, and Webb is showing us just how strange and varied celestial objects can be. It's expanding our concept of what's possible in the universe. Webb has also revolutionized our understanding of how water, essential for life as we know it, is distributed through the cosmos. In the protoplanetary disk around the star PDS-70, Webb detected water vapor in the inner disk, where rocky planets form. This is crucial because it shows that water can survive the intense radiation near young stars and be available for incorporation into forming planets. Even more exciting, Webb found that the water in planet-forming disks has the same ratio of regular water to heavy water, where hydrogen is replaced by deuterium, as water in our solar system. This suggests that the water in Earth's oceans has a direct connection to the water in interstellar space. The glass of water on your desk contains molecules that have been traveling through space for billions of years, largely unchanged since they formed in the cold depths between stars. Webb has also been studying cosmic collisions on the grandest scale, merging galaxy clusters. When galaxy clusters collide, they create the most energetic events in the universe since the Big Bang. The cluster MAX J0416, known as a cosmic collision in progress, showed Webb something remarkable: individual stars being ripped from their galaxies and scattered into intergalactic space. These orphaned stars, drifting between galaxies, create a faint glow called intra-cluster light. Webb's sensitive instruments can detect this ghostly light, revealing that up to half of all stars in galaxy clusters might be wandering homeless through space. It's a cosmic diaspora on an unimaginable scale, billions of stars exiled from their home galaxies, drifting through the darkness between islands of light. But these stellar refugees tell an important story. By studying their distribution and motion, astronomers can trace the history of cosmic collisions over billions of years. It's like forensic astronomy, reconstructing ancient galactic car crashes from the debris left behind. Webb is showing us that galaxy clusters are dynamic, violent places where entire galaxies can be torn apart by gravitational forces. One of Webb's most philosophically profound discoveries involves the fine-tuning of the universe. By observing distant supernovae and measuring cosmic expansion with incredible precision, Webb is helping us understand just how precisely balanced our universe is. If dark energy were just slightly stronger, galaxies would never have formed. If it were slightly weaker, the universe would have collapsed back on itself billions of years ago. This cosmic fine-tuning extends to many fundamental constants. The strength of gravity, the mass of electrons, the binding energy of atoms all seem precisely calibrated to allow the existence of stars, planets, and life. Webb's observations are confirming that we live in a remarkably special universe, raising deep questions about why the cosmos is the way it is. Some scientists invoke the multiverse, the idea that our universe is one of countless others, each with different physical laws. In this view, we naturally find ourselves in a universe compatible with our existence because we couldn't exist anywhere else. Others see evidence of design or purpose. Webb can't answer these ultimate questions, but it's providing the precise measurements that make them unavoidable. Webb has also discovered that galaxies can die in multiple ways. Some galaxies stop forming stars because they've used up all their gas, a slow starvation. Others have their gas stripped away by interactions with other galaxies, a violent death. But Webb found a third way. Some galaxies seem to shut down star formation from the inside out, possibly because their central black holes heat up the gas too much for it to collapse into stars. The galaxy GS9209 shows this process in action. Its center has stopped forming stars, while its outer regions still show some activity. It's like watching a city's lights go out from the center outward. Understanding how and why galaxies die is crucial for predicting the long-term evolution of the universe and the ultimate fate of our own Milky Way. Speaking of fate, Webb has been studying what happens to planetary systems when their stars die. Around the white dwarf WD 1856, Webb detected a disk of debris from shredded planets. As the star died and became a white dwarf, its planet's orbits destabilized, causing collisions that ground them into dust. It's a sobering preview of our own solar system's distant future. But Webb also found something hopeful. Some planets can survive their star's death. The white dwarf MOA2 010 BLG 477L has a giant planet still orbiting it, proof that not all worlds are doomed when their stars die. If humanity or our descendants still exist when the Sun becomes a white dwarf, we might be able to migrate to the outer solar system and continue our story around our star's fading ember. Webb has revolutionized our understanding of cosmic dust in another way by showing that it can act as a cosmic sunscreen. In star-forming regions, dust grains align with magnetic fields and polarize light, reducing the harmful ultraviolet radiation that reaches forming planets. This natural protection might be crucial for allowing complex molecules to form on young planets without being destroyed by their star's intense radiation. This discovery suggests that dusty environments, which astronomers once thought were hostile to life, might actually be protective nurseries. The dust that obscures our view might be essential for giving life a chance to develop. It's another example of how the universe seems to have built-in mechanisms that promote complexity and potentially life. One of Webb's most beautiful discoveries involves planetary nebulae in other galaxies. In the nearby galaxy, NGC 6822, Webb resolved individual planetary nebulae, the glowing shells of gas expelled by dying stars. Each nebula tells the story of a star's final moments, and Webb can read these stories from millions of light-years away. The variety is stunning. Some nebulae are perfectly spherical, suggesting the star died peacefully. Others show complex shapes, hourglasses, spirals, even rectangles, indicating turbulent deaths, possibly influenced by companion stars or planets. It's like a cosmic art gallery where each piece tells a story of stellar death and rebirth. Webb has also been studying the atmospheres of super-Earths, planets larger than Earth but smaller than Neptune. The planet LHS 475b, just 49 light-years away, showed something remarkable. Despite being tidally locked with one side always facing its star, it has an atmosphere that transports heat to the night side. This means even tidally locked planets might be more habitable than we thought. This discovery about heat transport on tidally locked planets opens up millions of new possibilities for habitable worlds. Red dwarf stars, which make up most stars in the galaxy, often have planets that are tidally locked. We used to think this made them uninhabitable. One side would be a scorching desert, while the other would be a frozen wasteland. But Webb is showing us that atmospheres can act like planetary circulation systems, moderating temperatures and potentially creating habitable zones even on these challenging worlds. Webb has also made a groundbreaking discovery about the early universe's chemical enrichment. In galaxy SPT 041847, which we see as it was just 1.5 billion years after the Big Bang, Webb detected a rich cocktail of heavy elements, including oxygen, nitrogen, and sulfur. But here's the surprise: the ratios of these elements don't match what we see in nearby galaxies. This suggests that the first generations of stars produced elements in different proportions than stars today. Perhaps the first stars were even more massive than we thought, or maybe they exploded in ways we don't fully understand. It's like finding an ancient recipe that uses different proportions of ingredients than modern versions. It tells us that cosmic chemistry has evolved over time. One of Webb's most exciting discoveries for the search for life came from studying the TRAPPIST-1 system more closely. While TRAPPIST-1b lacks a substantial atmosphere, Webb found that TRAPPIST-1c might have a thin atmosphere rich in carbon dioxide. Even more intriguing, the planets TRAPPIST-1, E, F, and G, all in the habitable zone, show hints of possible atmospheres. The key discovery is that these planets seem to have different atmospheric compositions despite forming from the same disk of material. This diversity is actually good news for life. It means that even in a single planetary system, nature experiments with different atmospheric recipes. Some might be too thick, some too thin, but some might be just right, what scientists call the Goldilocks scenario. Webb has also revealed that cosmic magnetic fields are more important than we realized. In the galaxy NGC 1068, Webb's polarization measurements showed that magnetic fields channel gas flows during star formation, acting like cosmic traffic controllers. These fields determine where stars form and how efficiently gas converts into stars. This matters because magnetic fields might be the universe's unsung heroes. They protect planets from harmful radiation, guide the formation of stars, and might even play a role in the development of life. Earth's magnetic field shields us from the solar wind. Without it, our atmosphere would be stripped away like what happened to Mars. Webb is showing us that magnetic fields shape the universe on every scale, from planets to galaxies. In a stunning discovery about stellar archaeology, Webb found ancient stars hiding in the heart of our galaxy that shouldn't exist according to our models. These stars have extremely low metal content, suggesting they formed when the universe was very young. But they're in the wrong place. Theory predicted such ancient stars should be in the galaxy's halo, not its center. This discovery is rewriting the history of our galaxy. It suggests that some of the first stars to form in the Milky Way migrated inward rather than outward, or that the galaxy's center formed differently than we thought. It's like finding ancient artifacts in unexpected places. Each discovery forces us to revise our understanding of history. Webb has also discovered that planet formation might be faster than we thought. Around the star HL Tauri, just 1 million years old, Webb detected gaps in the protoplanetary disk that indicate planets are already forming. 1 million years might sound like a long time, but in cosmic terms it's incredibly fast, like a baby learning to run before it can crawl. This rapid planet formation is good news for the prevalence of planets in the universe. If planets can form quickly, they're more likely to survive the chaotic early years of a stellar system. It also means that rocky planets like Earth might be common throughout the universe, increasing the chances for life. One of Webb's most mind-bending discoveries involves quantum effects on cosmic scales. In studying the polarization of light from distant galaxies, Webb found patterns that might indicate quantum entanglement between particles separated by millions of light-years. While this is still being debated, if confirmed, it would mean the universe is even more interconnected than we imagined. This cosmic entanglement wouldn't allow faster-than-light communication. Quantum mechanics forbids that, but it would mean that the universe is fundamentally non-local, with instantaneous correlations between distant regions. It's like discovering that the universe is one vast quantum system, with parts that are mysteriously connected across cosmic distances. Webb has also revolutionized our understanding of how galaxies feed. By detecting faint filaments of gas flowing into galaxies from the cosmic web, Webb showed that galaxies don't just consume their initial gas supply, they continuously feed on rivers of gas flowing in from intergalactic space. It's like discovering that galaxies are connected to cosmic feeding tubes that keep them alive and forming stars. This discovery solves a long-standing puzzle. How do galaxies keep forming stars for billions of years? The answer is that they're not closed systems. They're connected to the cosmic web, constantly receiving fresh supplies of gas. Our own Milky Way is feeding on gas streams right now, ensuring it can keep forming stars for billions of years to come. Webb's observations of these cosmic feeding streams revealed something even more remarkable. They're not pure hydrogen and helium from the Big Bang. They're already enriched with heavier elements from previous generations of stars. This means galaxies aren't just sharing gas, they're sharing the products of stellar evolution. It's a cosmic economy where galaxies trade the elements needed for planets and life. In one of its most technologically impressive feats, Webb has begun detecting the atmospheres of Earth-sized planets. The planet LHS 475b, roughly the same size as Earth, showed clear signs of having no atmosphere, or at most, an extremely thin one. While this particular world is too hot for life, the fact that Webb can study Earth-sized planet atmospheres at all is revolutionary. Think about what this means. We can now study worlds the size of Earth orbiting other stars, analyzing their atmospheres, molecule by molecule. We're living in the era when humanity can finally answer the question, Are there other Earths out there? Webb is the tool that's making this possible, turning science fiction into science fact. Webb has also discovered that some of the universe's most violent events might be more common than we thought. By detecting the afterglow of gamma-ray bursts, the most energetic explosions since the Big Bang, Webb found that these cosmic catastrophes might happen in unexpected environments. Some occur in relatively nearby metal-rich galaxies where theories said they shouldn't. This matters because gamma-ray bursts can sterilize large regions of space, potentially wiping out life on any nearby planets. If they're more common than we thought, it might help explain the Fermi paradox, why we haven't detected alien civilizations despite the vast number of potentially habitable planets. Perhaps life is regularly reset by these cosmic death rays. But Webb also found a silver lining. The heavy elements created by gamma-ray bursts are essential for rocky planets and life. Each burst enriches its galaxy with gold, platinum, uranium, and other heavy elements. It's another example of how the universe's most destructive events are also its most creative, forging the elements that make complex chemistry and life possible. In studying star formation, Webb made an unexpected discovery. Baby stars can be cannibals. In the Perseus star-forming region, Webb caught young protostars in the act of consuming smaller stellar embryos. It's survival of the fittest on a cosmic scale, with larger protostars growing at the expense of their smaller siblings. This stellar cannibalism might explain why we see fewer brown dwarfs than expected. Many might have been consumed by their larger neighbors before they could fully form. It also suggests that our Sun might have had siblings that it consumed during its formation, a disturbing thought that adds a darker chapter to our star's origin story. Webb has also revealed that the universe's first black holes grew in ways we never imagined. By detecting extremely red, dust-obscured quasars in the early universe, Webb showed that many early black holes were hidden from our view. They grew inside cocoons of dust and gas, invisible to optical telescopes but blazing brightly in infrared. These hidden black holes might solve the mystery of how supermassive black holes grew so large so quickly. If many were hidden, we've been underestimating how common and how active early black holes were. It's like discovering a hidden population that changes our entire census of the early universe. One of Webb's most beautiful discoveries involves cosmic light echoes. When a star explodes or a black hole flares, the light travels outward, illuminating surrounding dust clouds in sequence. Webb can watch these light echoes propagate through space, creating a three-dimensional map of the dust around cosmic events. In the case of the star Eta Carinae, which experienced a massive eruption in the 1800s, Webb can still see light from that event echoing off dust clouds light years away. It's like cosmic archaeology, using old light to study both the event and its surroundings. These light echoes are teaching us about the three-dimensional structure of space in ways we never could before. Webb has also discovered that some planets might form in impossible places. Around the black hole Sagittarius A star, at the center of our galaxy, Webb detected what might be protoplanetary disks. The idea that planets could form in the extreme gravitational and radiation environment near a supermassive black hole challenges everything we thought we knew about planet formation. If confirmed, these black hole planets would experience time dilation, gravitational waves, and radiation levels unlike anything in our solar system. They might be the most exotic real estate in the universe. While almost certainly lifeless, they prove that the universe's creativity in making worlds exceeds our wildest imagination. In one of its most profound discoveries, Webb has begun detecting the building blocks of life in unexpected places. In the atmosphere of exoplanet WASP 80b, Webb found both methane and carbon dioxide existing together in a chemical equilibrium that, on Earth, would require life to maintain. While this planet is far too hot for life as we know it, it shows that lifelike chemistry might be more common in the universe than we thought. Webb also detected complex organic molecules in the disks around young stars, including molecules that on Earth are associated with biological processes. While these molecules can form without life, their widespread presence suggests the universe is naturally equipped with life's building blocks. It's as if the cosmos has a built-in tendency toward the chemistry of life. Perhaps most remarkably, Webb has detected phosphorus, a key element for life in the Crab Nebula, the remnant of a star that exploded in the year 1054. Phosphorus is essential for DNA, RNA, and cellular energy transfer, but it's relatively rare in the universe. Webb's observations show that supernovae are efficient phosphorus factories, solving another piece of the cosmic life puzzle. This discovery completes the cosmic recipe for life. We now know where every essential element comes from: hydrogen from the Big Bang, carbon and oxygen from dying stars, phosphorus from supernovae, and complex molecules from the chemistry of space itself. Webb is showing us that the universe isn't just capable of producing life, it seems almost eager to do so. Webb has also transformed our understanding of cosmic time. By observing galaxies at different distances, Webb can see the universe at different ages, creating a time-lapse movie of cosmic evolution. But here's the mind-bending part. Because the universe is expanding, the most distant galaxies Webb sees are now much farther away than they appear. Some are now over 30 billion light-years from us, even though the universe is only 13.8 billion years old. This cosmic expansion means that there are galaxies we can see today that future astronomers will never be able to observe. The accelerating expansion of the universe is carrying them beyond our cosmic horizon. Webb is capturing images of galaxies that are taking their final bow on the cosmic stage, at least from our perspective. We're witnessing the last light from billions of galaxies that will soon fade forever from view. But perhaps Webb's greatest discovery isn't any single observation. It's the revelation of just how much we still don't know. Every answer Webb provides raises 10 new questions. Why do early galaxies look so mature? How did supermassive black holes grow so fast? Why is the universe's expansion accelerating? What is dark matter? What is dark energy? These aren't failures, they're invitations to keep exploring. Science progresses not by answering all questions, but by discovering better questions to ask. Webb is showing us that the universe is far stranger, more complex, and more wonderful than our current theories predict. It's humbling and exciting at the same time. Webb has also shown us that we're living in a special time in cosmic history. We exist in the brief era when galaxies are visible, stars are shining, and planets can support life. In the far future, the universe will be a much darker, emptier place. In the distant past, it was too hot and chaotic for complexity to exist. We live in the cosmic sweet spot, the Goldilocks epoch of the universe. This temporal privilege comes with a responsibility. We might be among the only beings in the universe capable of understanding and appreciating the cosmic story. Through instruments like Webb, we're the universe's way of comprehending itself. Every discovery Webb makes is the cosmos revealing its own secrets through human curiosity and ingenuity. Looking at Webb's discoveries as a whole, a profound pattern emerges. From the largest scales of galaxy clusters to the smallest molecules in planetary atmospheres, the universe shows a tendency toward increasing complexity. Simple hydrogen and helium become stars. Stars create heavy elements form planets Planets develop atmospheres, and sometimes, just sometimes, those atmospheres cradle life that can look back and understand it all. Webb is revealing that this isn't an accident. The laws of physics seem fine-tuned to allow complexity to emerge. The universe could have been simpler, just a soup of particles or black holes or empty space. Instead, it's a magnificent hierarchy of structures, from subatomic particles to galaxy superclusters with life and consciousness emerging in between. Every atom in your body, every thought in your mind, every emotion you feel is part of this cosmic evolution. You're not separate from the universe. You're a particularly complex and self-aware arrangement of cosmic material. When you look at Webb's images, you're literally the universe observing itself, marveling at its own beauty and complexity. This cosmic perspective that Webb provides is more than just scientific knowledge. It's a new way of seeing our place in existence. We're not insignificant specks in a vast, uncaring cosmos. We're the universe's way of experiencing wonder, love, curiosity, and understanding. We're how the cosmos writes poetry, composes music, and asks why. As I reflect on Webb's discoveries, I'm filled with profound gratitude. Gratitude that we live in an age where such observations are possible. Gratitude for the thousands of scientists and engineers who made Webb possible. And gratitude for you watching this video, sharing in the wonder of discovery. The James Webb Space Telescope has shown us that we live in a universe far grander and more mysterious than we imagined. It's revealed baby galaxies from the cosmic dawn, detected potentially habitable worlds, and found the building blocks of life scattered throughout space. But most importantly, it's reminded us that we're part of an ongoing cosmic story, a story of matter organizing into ever greater complexity, eventually producing beings capable of understanding their own origins. So the next time you look up at the night sky, remember, you're not just looking at distant lights. You're looking at your cosmic family tree, your stellar ancestors, and maybe even your distant cousins on worlds we've yet to discover. Thanks to Webb, we know that the universe is not just vast and ancient. It's creative, dynamic, and filled with possibilities we're only beginning to imagine. Keep looking up, keep wondering, and remember, we are all made of star stuff, connected across space and time in the greatest story ever told, the universe's story, our story. And thanks to the James Webb Space Telescope, we're reading new chapters of that story every single day. And I am sure you will love this next video on the left side of the screen. This is why we will never leave the Milky Way. Learn how special relativity, dark energy, time dilation, and cosmic radiation make escaping our galaxy impossible, even with advanced technology like warp drives, wormholes, or antimatter engines. See you there.